Hello everyone and welcome back to my channel. Today's tutorial is on data preparation for machine learning models. If you are aiming to build effective and reliable machine learning models, then data preparation is a crucial step for you. In this video, we'll dive into several key aspects of data preparation: handling missing values, removing duplicates, normalization, data sampling, and dimensionality reduction. So let's get started. Did you know that data scientists spend up to 80% of their time just cleaning and preparing data before they even get to the fun part of building models? It's like being a chef who spent most of their time chopping vegetables and only a fraction actually cooking the dish. But just like in cooking, if you skip the prep work, the end result won't be nearly as satisfying. That's why data preparation is such a crucial step in the machine learning process. And today, we're going to dive into the key techniques to get your data ready for action. First, let's talk about handling missing values. Missing data is a common issue in datasets. Before dealing with missing data, we should attempt to understand why data is missing. There are several reasons why data could be missing. They include changes in data collection methods, human errors, bias, or simply lack of reliable input. And how you handle it can significantly impact the performance of your machine learning models. There are several strategies you can use. The simplest is to remove any rows or columns with missing values. However, this approach can lead to the loss of valuable data, especially if the missing values are sparse. Probably you are wondering, what do you mean by sparse values? It means that a significant number of elements are zeros or missing. A more refined approach is to impute the missing values. This could be done by filling them with mean, median, or mode of the column, or using more sophisticated methods like KNN Imputation or model-based imputation. Let's explore when each method is used. Mean imputation is generally used for continuous numerical data, where the missing values are likely to have a distribution similar to the non-missing values. Mean imputation works the best when data is symmetrically distributed, as the mean is a good measure of central tendency in such cases. Suppose you have a dataset of house prices and one of the columns is the size of the house in square feet. If some of the values in the column are missing, you might impute the missing values with the mean size of the house, because the mean is a representative value of the dataset, especially when the data is normally distributed. Median imputation is also used for continuous numerical data. It is preferred when the data is skewed, because the median is a better measure of central tendency in such cases. Skewed data refers to the distribution of data that is not symmetrical. In a perfectly symmetrical distribution, the left and the right side of the data's histogram are mirror images of each other. However, in skewed distributions, one tail of the data is longer or more stretched out than the other. We know two main types of skewness: right skewed, positive skewness; left skewed, negative skewness. If you want a detailed course about statistics for data science, even though I'm not a professional statistician, I can share with you my knowledge if you leave a comment below. Let's discuss an example of median imputation. Suppose you have a dataset containing the salaries of employees in a company and some salary values are missing. Salaries are often right skewed. Few people earn much more than the rest, so imputing missing salary with the median salary would be more appropriate, because the median is not influenced by extreme values, outliers, making it a more robust choice in skewed distribution. Mode imputation is mainly used for categorical data, where the mode represents the most common category or value. It's useful when there is a frequent or dominant category in your dataset. Imagine you have a dataset of survey responses and one column records the preferred mode of transport. Example, car, bus, train, and so on. If some entries are missing, you might impute the missing values with the most common mode of transport. As I explained, the mode represents the most typical value, so it makes sense to impute missing values with it in categorical data. KNN imputation is used when the data has a complex relationships or patterns that can be leveraged to predict missing values, and it can be used for both categorical or numerical data. This method is particularly useful when the missing values can be better estimated using the relationships with other variables in the dataset. Suppose you have a dataset with multiple features, including age, income, and spending score, but some ages are missing. KNN imputation would find the nearest neighbor based on the similarity of non-missing features, income and spending score, and then impute the missing age value as the average of the ages of these neighbors. KNN considers the surrounding context and can capture more complex patterns in the data, leading to more accurate imputations. In summary, mean imputation are used for numerical data when the data is symmetrically distributed. Mean imputation used for numerical data when the data is skewed or has outliers. Mode imputation is used for categorical data where specific value is predominant. KNN imputation used for both numerical and categorical data when you want to leverage relationships or patterns between multiple features for more accurate imputations. Each method has its own strengths and is suited for different types of data and missiness patterns. Choosing the right imputation method depends on the specific characteristics of your dataset. It's essential to choose the strategy that best suits the nature of your data and the problem you're trying to resolve. Let's start with handling missing data using Python's Pandas library. Missing values are common in any dataset, but by the end of this tutorial, you will know exactly how to handle them like a pro. Let's dive in. First things first, how do you spot missing data? We'll use a more complex dataset for this tutorial, which includes students' information like names, ages, scores, addresses, and more. Let's load the data and identify any missing values using isNull method. So here we go. We import data. Here's our dataset, which includes a mix of numeric and text data, along with some missing values. To identify any missing values, we can use the isNull method. The isNull method returns a data frame where each cell is marked true if the value is missing and false if it isn't. The mask will help us pinpoint exactly where the data is missing. Let's identify rows that contain any missing values. This is important when deciding whether to keep or remove certain rows. By using .any axis equal 1, we can filter out rows that have at least one missing value. This gives us a focused view of where data might be incomplete. Sometimes, it's best to remove rows with missing values entirely, especially if they have multiple missing values. Here's how to do that. In this example, any rows with a missing value is completely removed. This method is easy but can result in losing a significant amount of data, so use it wisely. Now, what if you only care about missing values in a certain column? For instance, let's drop rows where the math score or science score are missing. Here, only rows where math score or science score are missing are removed. This approach allows you to focus on the most important columns while retaining as much data as possible. In some cases, you might want to drop entire columns instead of rows, especially if a column has too many missing values to be useful. Using drop in A axis equals 1, we remove any column that contains a missing value. This method is effective, but be careful. Dropping too many columns might leave your dataset lacking critical information. Finally, let's say you want to drop the column with the most missing values. First, we need to identify that column. Here, we calculated the number of missing values in each column and used IDX max to find the column with the highest number of missing values. We then drop it just that one column, which is the zip code. This is a smart way to clean your data while preserving as much information as possible. But what if you don't want to lose valuable information by dropping rows or columns? That's where imputation comes in. In this part of the tutorial, I will show you how to replace missing values with more meaningful data instead of simply removing them. Let's jump right into it. As we explained earlier, imputation is a powerful technique that allows you to fill any missing values with substitutes, ensuring your dataset remains as complete as possible. This is especially useful when you have a lot of missing data and don't want to lose entire rows or columns. We'll be using the same student dataset from earlier, but this time we'll focus on filling in those gaps rather than removing them. Let's create a copy of the original data frame to work with. This is a good practice when experimenting with data cleaning, as it keeps the original dataset intact. Let's start by imputing the missing values in categorical column. For example, the name column might have missing values. One simple approach is to replace the missing names with the most common name in the dataset. Here's how it works. First, we use mode 0 between brackets, which finds the most common values in the name column. We then use fill NA to replace all missing names with this value. This technique is simple but effective, especially when missing data is minimal. So you can see that the name column doesn't have any missing values. Next, let's handle missing values in a numeric column. The age column, for instance, might have some gaps. A common practice to replace missing numeric values is with the mean of the column. In this code, we calculate the mean of the age column using .mean. Then we use fill NA again to replace missing ages with the average value. This method ensures that the central tendency of the data remains consistent even after imputation. You can do the same to math score, science score, and English score. Sometimes you want to replace missing values based on the other related data. For instance, if a student's zip code is missing, you might want to infer it based on their address. This is known as conditional imputation. Let's fill in the missing zip code values based on the address column. In this example, we create a dictionary address zip mapping that matches each address to the corresponding zip code. Then we use the .apply method to go through each row and fill the missing zip code values based on the address. If a zip code is missing, the code looks up the address in the dictionary and fills it in the appropriate zip code. This approach is more sophisticated and helps maintaining the relationship between the columns, ensuring that your data remains logical and consistent. But what if you want to use more advanced method to predict missing values based on the nearest neighbors? That's where k-nearest neighbors, KNN Imputation, comes in. In this final section, we'll dive into how to use KNN to fill in those gaps. Let's get started. K-nearest neighbors, or KNN Imputation, is a more sophisticated technique that fills in the missing values by considering the value of the closest data point in the dataset. Essentially, it looks at the most similar data points and uses them to predict the missing values. This method is particularly useful when the relationships between features are complex and linear imputation might be not sufficient. To perform KNN imputation, we'll use the KNN imputer from the scikit-learn impute model. But first, let's install the required library and then apply KNN imputation to our dataset. After installing the scikit-learn library, we can proceed with importing the necessary model for applying KNN imputation to our dataset. Here's what's happening. We first create a list of the columns we want to impute using KNN. Then we initialize the KNN imputers and specify the number of neighbors. N neighbors equals 5. It should consider for imputing the missing values. Finally, we apply this imputation to the selected column in our dataset. Let's take a look at the results. As you can see, the missing values have been replaced with values that reflect the overall patterns in the data. KNN Imputation is a great tool when you need a more accurate and data-driven way to handle missing values, especially in large and more complex datasets. And that wraps up our deep dive into handling missing data with pandas. Whether you're dropping data using simple imputations or leveraging advanced techniques like KNN, you now have a solid toolkit for ensuring your datasets are as complete and reliable as possible. Next, let's talk about deleting duplicates. Duplicates data can introduce bias in your model and lead to inaccurate predictions. Identifying and removing duplicates in trees is a crucial step in data cleaning. Duplicates can be exact copies of rows or subtle variations that require more careful detection. When you remove duplicates, you reduce redundancy, ensuring that your model learns only from unique and relevant data. When handling duplicated data, especially for textual data, it's a good practice to look for near duplicates. Near duplicates refer to records in the dataset that are not exactly duplicates, but are very similar to each other. The records might represent the same entity, such as a person, company, or a product, but with slight variation or inconsistencies in how the data has been entered. Near duplicates are common in datasets, especially when data is collected from multiple sources or entered manually. Near duplicates can be either minor variation, like Trondo or 123 element street. Here we have a difference in spelling and a difference in data entry. It can also be incomplete data. For example, one record has a phone number and the other does not. It could be a typographical error, like a small typing mistake that results in slightly different entries. The same information can be represented in different ways, for example, dates. Detecting near duplicates can be challenging. It often requires more sophisticated techniques than a sample duplicate detection. Tools like fuzzy matching, similarity scores, or machine learning algorithms are often used. After identifying near duplicates, we must make a decision about how to handle them. Like we can either merge records, choose one record, or flag for a review to manually review, especially when merging could lead to data loss. Handling near duplicates can be done with multiple methods. For example, fuzzy matching. Use algorithms that measure the similarity between strings or other data types to identify near duplicates. Manual review. For small datasets, manually reviewing near duplicates might be the best option. Standardized format like address, name, and dates before comparing records to reduce likelihood of near duplicates. Automated tools. Use data cleaning tools and software that can automatically identify and manage near duplicates. Now, we will be diving into key aspects of data cleaning. Detecting duplicates and near duplicates in a dataset. We're going to use Python along with libraries like pandas, fuzzy, and scikit-learn. I'll be working with the dataset of Spotify tracks, which is great for this kind of analysis. Now I'll show you how to both detect exact duplicates and use techniques like fuzzy matching and cosine similarity to find near duplicates. First, we need to load our dataset. For this tutorial, I'm using the Spotify tracks dataset, which you can find on Kaggle. After download it, we'll load it into Pandas data frame. Let's take a look at the first rows to get an understanding of the data. Here we can see columns like track name, artists, and popularity. For our analysis, we'll focus on the track name and artist columns to detect duplicates. Let's start by identifying exact duplicates. We'll check for duplicate combinations of track name and artists. This is useful when the tracks are repeated in the dataset under the same artist name. As you can see, we've detected a few exact duplicates. To clean up the dataset, we can drop these duplicates easily with pandas. Now, let's move on detecting near duplicates. This is where the titles or artist names are slightly different but likely represent the same entry. We'll use the Fuzzy Wuzzy library for fuzzy string matching. In this case, let's check for songs similar to Shape of You. Here we go. We found tracks that are similar to Shape of You. Fuzzy matching is great for handling minor variations in names, such as spelling errors or formatting differences. Next, I will show you how to detect near duplicates using cosine similarity, which is a mathematical way to compare the similarity of two pieces of text. We'll use TF-IDF to vectorize the song titles and then calculate the cosine similarity between them. This matrix shows the similarity scores between different songs. The closer a score is to 1, the more similar the titles are. You can use this to detect near duplicates in large text and in large datasets. We'll use a threshold to define how similar two songs need to be to consider them near duplicates. We'll set this threshold to 80%, meaning songs with similarity score of 80% or higher will be considered near duplicates. Using this code, we can find pairs of tracks that are considered near duplicates based on their cosine similarity scores. Cosine similarity score. This is a powerful technique to detect duplicates when the titles are not exactly the same, but are very similar. And that's it. You have learned how to detect both exact and near duplicates in a dataset using Python. We explored simple duplicate detection with pandas, fuzzy matching with Fuzzy Wuzzy, and advanced near duplicate detection with cosine similarity. These techniques are essential for data cleaning and preparation, especially when dealing with large, messy datasets. Now let's discuss handling outliers. Outliers are data points that deviate significantly from other observations that can occur due to variability in the data, measurement errors or experimental errors. Outliers can skew your model's results, leading to poor performance, especially in algorithms like linear regression. There are few ways to handle outliers. You can remove them, transform the data to reduce their impact, or use robust algorithms that are less sensitive to outliers. The approach you choose depends on whether the outliers are genuine or erroneous and on the specific goal of your analysis. So transforming data is one of the tools to handle outliers, which leads us to our next section, data normalization. Normalization is another aspect of data preparation for machine learning models, particularly those that rely on distance metrics like k-nearest neighbor or gradient descent-based algorithms, which perform better when features are on similar scale. Normalization involves rescaling data so that it fits within a specific range, usually between 0 and 1, or adjusting it so that the mean is 0 and the standard deviation is 1. This process ensures that no single feature disproportionately influences the model due to its scale. Given an original value of v of feature f, the normalized value of the feature v prime is computed as v minus the feature mean, denoted as f bar, divided by the standard deviation of the feature, sigma f. To illustrate how z-score normalization works, let's consider the feature with 5 values shown here. The mean of these values is 40,800, and if the deviation is 33,544, to normalize the fourth value we subtract 40,800 from 40,000 and divide the result by 33,544. These yield a negative 0.024. Using the same approach for the other values of the feature, the normalized value will be minus 0.859, minus 0.5, minus 0.322, 0.024, and 1.705. Note that the mean of the normalized values is 0 and the standard deviation is 1. In most instances, Z-score normalization works well. However, some problems and certain machine learning algorithms require that our data have lower and upper bounds, such as 0 and 1. For that, we need min-max normalization. With min-max normalization, we transform the original data to a new scale defined by user-defined lower and upper bounds. Most often, the new boundaries and values are 0 and 1. Mathematically, this transformation is represented as shown here, where v prime is a normalized value, v is the original value, min f is the minimal value of the feature, max f is the maximum value of the feature, upper f is a user-defined upper bound, and lower f is a user-defined lower bound. To illustrate how min-max normalization works, let's consider the same set of 5 values. Assuming that we set the upper bound to 1 and the lower bound to 0, to normalize the third value, 30,000, we apply the min-max normalization formula, which yield 0.209. Using the same for the remaining 4, the min-max normalized values for the feature will be 0.209, 0.326, and 1. Z-score and min-max normalization are usually suitable when there are no significant outliers in our data. If there are outliers in our data, a more suitable approach is log transformation. With log transformation, we replace the values of the original data with its logarithm as shown here, where v is the original value for the feature and v prime is the normalized value. The logarithm used for log transform can be the natural logarithm log base 10 or log base 2. This is generally not critical. However, it's important to note that log transformation works only for values that are positive. Applying log transformation to the fifth value, in our example data, we get 4.991. Applied to the rest values, we now have 4.079, 4.380, 4.477, 4.602, and 4.991. Notice that this approach minimizes the distance between the original outlier values, 12,000 and 98,000, and the rest of the data. When working with datasets, you'll often find that different features have different scales. For example, one feature might represent age in years, ranging from 1 to 100, while another might represent income, ranging from few hundreds to millions. Feeding these features into a machine learning model as is can cause the model to assign undue importance to the larger values, leading to biases or skewed predictions. Normalization helps by scaling these features to a common range, ensuring that each feature contributes equally to the model. There are several techniques to achieve this, including the z-score normalization, min-max normalization, and log normalization, each serving different purposes based on the nature of your data. So how do we apply these techniques? Now that we understand the theory, let's jump into the practice part, implementing normalization techniques in Python using a real dataset. First up, let's tackle z-score normalization, also known as standardization. Remember, this method transforms your data to have the mean of 0 and a standard deviation of 1. It's particularly useful when your data has outliers, as it handles them more gracefully compared to other normalization techniques. So first, let's import our data. We load the dataset into a pandas data frame called data. The dataset is stored as CSV, separated value file. So we use the pd.readCSV function to read the CSV file from the web and converts it into a data frame, making it easy to explore and manipulate. Let's show up the first rows in this dataset. As you can see, it contains historical data on the number of airline passengers per month. This dataset is often used for time series analysis, but here we're focusing on a particular column, the number of Here, you're extracting the passengers column from the data frame and storing it in a new data frame called passengers data. The double squared brackets indicate that you're selecting this column as a data frame, not as a series, a one-dimensional array. This distinction is important for later operations where you might need a two-dimensional structure. Why this column? You might ask. Simply because in this dataset, the passengers column represents the number of passengers each month, which will normalize. Normalization will help standardize this feature, making it easier for machine learning models to process. We first import the standard scalar method from scikit-learn.preprocessing model. Then, we define a scalar as follows. Scalar equals standard scalar. This creates an instance of the standard scalar class, which we will use to apply z-score normalization to the data. Here, this method does two things. First, fit. It calculates the mean and standard deviation of the passenger's data. Then it standardizes the data by subtracting the mean and dividing by the standard deviation using transform. This way, it's effectively transforming the data to have the mean of 0 and the standard deviation of 1. The result scaled data is an array of the normalized data. Each value in scaled data represents the number of standardized according to the z-score normalization formula, where x is the original value, mu is the mean, and sigma is the standard deviation. This line creates a new column in the original data called passengers z-score. It stores the z-score normalized values in this column. This allows you to keep the original data intact while also having access to the normalized data. Let's display the updated data frame. Adding the normalized data back to the data frame makes it easy to compare the original and normalized values side by side, which is helpful for analysis and model building. We can also plot the differences between the column before and after normalization as follows. After normalization, we notice that both plots show similar trends and seasonality. The normalization process has not altered the pattern of the data, it has only changed the scale. In the right plot, these scores indicate how many standard deviation each point is from the mean of the dataset. A z-score close to 0 means the value is near the mean, while a positive and negative z-scores indicates how far above or below the mean the value lies, respectively. Next, we have mean-max normalization, a simple yet effective technique that scales your data to a fixed range, usually between 0 and 1. This method is particularly useful when you know your data will always lie within a specific range. Let's find how to apply min-max scalar using Python. First, we import the required library. This line imports the min-max scalar class from the scikit-learn.processing model. Scikit-learn or sklearn is a popular machine learning library in Python that provides a wide range of tools for data processing, model building, and evaluation. The min-max scalar is a specific tool used to apply min-max normalization to data. First, we create an instance of the min-max scalar class. The min-max scalar transforms features by scaling each feature to a given range, typically between 0 and 1. This is done by adjusting the data according to the following formula, where x is the original value, x-min is the minimum value of the feature, maximum value of the feature, and scaled is the resulting normalized value, which will lie within the specific range. By default, it's between 0 and 1. Next, we need to use fit transform method again. The fit method calculates the mean and the maximum of the passenger data column or the data frame if more than one column were selected. These values are then used to scale the data. Then transform method applies the min-max scaling to each value in the passenger data frame, producing the scaled data, which is stored in min-max scaled data. The result is that each value in min-max scaled data now lies between the range of 0 and 1, where 0 corresponds to the original minimum value and 1 corresponds to the original maximum value of the column. Then we add the new column to the original data frame data, name it passengers min-max. This new column contains the min-max normalized values of the passengers data. By doing this, we preserve the original data while also having the normalized data available in the same data frame for comparison or further analysis. Finally, we can call the head method to display the first rows of the data frame. It's a quick way to verify that the min-max normalization was applied correctly and that the new column passengers min-max has been added to the data frame. We can see from the plot that both plots show the same overall pattern, which indicates that the min-max normalization has not altered the relationship between data points. It has simply rescaled them. So we can also see that min-max normalization effectively compresses the original data into 1-0 range, maintaining relative distance between data points. This is beneficial in scenarios where you need to ensure that all features contribute equally to the model. Finally, let's explore log normalization. This technique is ideal when your data spans several orders of magnitude, as you want to compress these ranges. It's particularly effective for skewed distributions, so let's find out how can we compute log normalization. The log1p function from NumPy computes the natural logarithm of 1 plus the input array element-wise. Why log1p? Instead of when you apply a logarithm transformation to data, using log1p instead of log helps avoid issues when the data contains 0 or very small values. For example, if you try to compute log 0, you would encounter an undefined or negative infinity error. Log1p adds 1 to the data first, which shifts the range of values and ensures the logarithm is well defined for all non-negative inputs. The purpose of log transformation is often used when data spans several orders of magnitude or when the data is highly skewed. It compresses the range of data, reducing the impact of large values and making the data more normally distributed. This is particularly useful for the machine learning models that assume or perform better with normally distributed data. The code applies log normalization to the passenger data and stores the result transformed values in the new column named passengers log within the data frame. In this final example, we applied log normalization to the passengers column. Notice how the transformation compresses the large values, which can be particularly useful when dealing with skewed data. Now, let's move into data sampling for machine learning to understand its importance for building a strong model. As we get our data ready for machine learning, we need to either decrease the number of rows or divide the dataset into 2 or more segments. This is necessary because the data could be too large or intricate to work with it in its existing state. Or we might want to reserve some data for future use. In supervised machine learning, our objective is to develop a model that correlates a specific input, referred to as independent variables, within an associated output, known as the dependent variable. To accurately assess whether our model is learning, we need an unbiased estimation of its performance using data it hasn't encountered before. This involves dividing our previously labeled historical data into training and testing datasets. We reserve the test data while using the training data to build or train our model. Subsequently, we evaluate our model's performance with the test data. There are various methods to split the data for this purpose. with sampling being the most widely used approach. The most prevalent method is called sampling. This process involves choosing a subset from a dataset to represent the entire group. In statistical terminology, the complete dataset is referred to as the population, while the selected portion is termed a sample. There are various types of sampling techniques available. To demonstrate some of these concepts, let's consider a fictional group of 20 students, 12 women and 8 men. From this group, we will select a sample of 5 students. The initial sampling method we present is random sampling without replacement. In this method, we start by randomly choosing a student from the overall population. For instance, we begin by choosing student number 6, followed by student 4. It's important to note that once we select a student, they are removed from the pool of available candidates. Next, we select student 11, then student 10, and finally, we conclude with student 20. This is random sampling without replacement. The next type of sampling is called random sampling with replacement. In this method, we continue to randomly select students from the population, but there is a significant difference. Before I reveal what it is, let's see if you can identify it by yourself. We'll start by randomly picking the first 4 students. The selection are student 11, followed by student 7, then student 6, and finally student 14. Have you noticed anything different yet? I'm sure you have. As we choose students from the population, they remain available for selection in future trials. This aspect is what we refer to as replacement in random sampling with replacement. Consequently, this means we could end up selecting the same students multiple times for our sample. Indeed, that's what occurs in this example, as student 11 is chosen twice. While the sampling method may seem unusual, it is actually a crucial technique in machine learning known as bootstrapping. Bootstrapping is commonly utilized to assess and estimate the performance of features in a supervised machine learning model, especially when we have limited data. The following sampling method is referred to as stratified random sampling. This approach is an adaptation of simple random sampling and guarantees that the distribution of values for a specific characteristic within the sample aligns with that of the overall population. To achieve this, the instances in the original dataset or population are first categorized into homogeneous subgroups known as strata. For instance, if we choose to stratify based on gender, we must first organize our population by gender. Our objective is to create a sample of 5 students from a total of 20 students in the population, meaning our sample should represent a quarter of the population. It also implies that our sample must consist of quarter of the students from each stratum. Given that there are 12 women in the population, we randomly select 3 women from our sample. Additionally, with 8 men in the population, we randomly choose 2 men. This results in a sample that reflects the same 3:2 gender ratio of women to men as the overall population, highlighting the advantage of this sampling technique. Before training the supervised machine learning model, it's essential to divide our data into training and test sets using various sampling methods. To demonstrate the data splitting process, let's import and take a look at a dataset that tracks customer loan information from 2022 to 2024. Prior to splitting the data, we need to first isolate the dependent variable y from the independent variable x's. Assuming that the decision column indicates whether a customer receives a loan, we can create a data frame called y that focuses solely on that column. To do this, we first define a string variable named response to represent the dependent variable column, which is decision. Then, we generate our data frame by subsetting according to this variable. Finally, We take a moment to preview our data frame. Let's go ahead and run this. To create a data frame of the independent variables, we can either use the list of the column we want to select, as before, predictors. So, to create a list of predictors, we start by using the list command. This action provides us with all the columns from the lone decision dataset. Next, we eliminate the decision column from the list. We use the remove method to take out the decision column, leaving us with all the other columns. With our predictors in place, we can now generate a data frame named X, which consists of the remaining independent variable. We can then preview the X data frame. A straightforward way to accomplish this in one single line of code is by employing the drop method in pandas as follows. We drop the decision column and then we review the outcome. Perfect! The initial method we use to divide our data is straightforward, random sampling without replacement. We can use the train test split from the scikit-learn model selection subpackage to achieve this. Now, let's go ahead and import it. Next, we input our dependent variable x and dependent variable y into the function that handles our datasets. We designate these datasets as xtrain, xtest, ytrain, ytest. The xtrain data frame contains the independent variable for the training set, consisting of 750 rows and 6 columns. The ytrain data frame holds the dependent variable for the training set, also with 750 rows and 1 single column. The xtest data frame comprises the independent variable for the test set, containing 250 rows and 6 columns. Lastly, the ytest data frame consists of the dependent variable for the test set, which includes 250 rows and 1 single column. The original dataset contains 1000 rows, which means that the 250 rows in the two test sets account for 25% of the total data. By default, the train test split function assigns 25% of the original dataset to the test set. If we wish to change this default setting, we can do so by adjusting either the train size argument or the test size argument within the function. For example, we can allocate 40% of the original data to the test set as follows. Within our train test split function, we specify in addition an argument called test_size, and we set it to 0.4. We see that 400 rows are now assigned to the test set. That is 40% of the 1000 rows from the original dataset. The second method we employ to divide our data is stratified random sampling. This approach aims to preserve the same distribution of values for a particular column in both the original training and testing datasets. To compare the two sampling methods, let's perform another split using simple random sampling. This time, we will allocate 1% of the original data to the test set. It's important to know that we also specified the random state argument in our code. This ensures that the result of this tutorial can be consistently reproduced by both you and I in the future. Our objective for using stratified random sampling is to maintain the same distribution for the value purpose column between the original training and testing datasets. Then, let's get the distribution for the purpose column in the original data. We do this by using X. We specify the column we want, which is purpose, and we get the value counts. Within the value counts method, we specify normalize equal to true, and that gives us the distribution of values for the purpose column. We do the same for the test set, which was created based on simple random sampling. We use then x underscore train test. We specify the column we want, which is purpose, then the value counts method, and we specify that normalize is equal to true. Let me get the distribution. Looking at the two distribution, we notice that there is a noticeable difference in the values. Now let's split the data using stratified random sampling, stratifying by purpose. To do so, we specify an additional argument, which is stratify, and we specify the column we want. We want to stratify by, which happens to be the purpose column, and we can run our code. Once again, we can get the distribution of the purpose column within the test data. Looking at these two distributions, X test and the original X purpose distribution, we can see the distribution of values for the purpose column in the test set created by stratified random sampling more closely mimics the original data above. Now, we're going to explore a common pre-processing step used in machine learning, which is splitting data into training and testing sets with stratified sampling using R. We'll use a dataset related to customer loan decisions. First, we'll start by loading the necessary libraries. In R, we'll use reader for reading data, dplyr for data manipulation, and caret for splitting the data. Always remember, if you want to install any of these packages, you can use install.packages and then specify the name in between parentheses as follows. Next, we load the dataset using readCSV function. In this tutorial, we're using a file called customerloandata.csv, and we can also display the first row of this data frame. Let's go ahead and run this. Note that this is the right form of readCSV method. In this dataset, the column decision is target or response variable. We'll isolate this into a separate variable called y. To do this, we first specify the response variable. Then we extract the column decision using the function select, and then we display the first rows. The following error is related to a problem in the dplyr package. We can try to install it again. And there you have it, problem resolved. So we have here the first rows of the y data frame. Now we need to separate the predictor variables, which means all the columns except the response variable. We can do this by using predictors, as we name the variable, and then set different names gf and response. Then we create the value x, or the data frame x, of independent variable. Select. Then we display the first rows. Let's run this. There must be a problem. And there you have it. So a crucial part of building machine learning models is splitting the data into training and testing sets. We'll use the create data partition function from the caret package to split the data. In this case, we'll do a stratified split based on the purpose column. So set seed to have the same results, train index is create data partition f per p equals point, and then we use these indexes to create the train set. There we have it, our two subsets. To make sure the stratified sampling works as expected, we can check the distribution of the purpose column in the test set. And you can see that the distribution is slightly symmetrical between our dataset and the testing dataset. That's it for this tutorial. We successfully loaded the data, defined predictors and response variable, split the data into training and test sets using stratified sampling, and verified the distribution. Now, let's discuss the last data preparation technique, which is dimensionality reduction. As we get our data ready for machine learning, it's often necessary to simplify or shrink the data size. There are various methods to achieve this. As we mentioned earlier, one effective approach is sampling, which allows us to decrease the number of rows in our dataset. Another method to consider is dimensionality reduction. True to its name, dimensionality reduction involves decreasing the number of features or dimensions within a dataset. This process is crucial in machine learning as it minimizes the time and storage needed for data processing. Additionally, it enhances data visualization and improves model interpretability while helping to prevent the curse of dimensionality. The curse of dimensionality is a concept in machine learning that refers to the decline in a model's performance as the dimensionality of the training data increases. As we add more features to our model, it becomes necessary to also increase the number of instances in the training data. If we neglect this, the performance of our model will gradually decline. The truth is that we cannot always significantly increase the number of instances in a particular dataset. Therefore, it's sometimes necessary to concentrate on reducing the dimensionality of our data to lessen the effect of the curse of dimensionality. In simpler terms, we must determine the ideal number of features to utilize. There are two prevalent methods for dimensionality reduction: feature selection and feature extraction. The concept of feature selection revolves around pinpointing the smallest set of features that can achieve model performance nearly equivalent to that of a model trained on all available features. The underlying assumption is that certain features or independent variables might be redundant or irrelevant, allowing them to be eliminated without significantly affecting the model's performance. This is why feature selection is often called variable subset selection. To demonstrate how this operates, let's consider our objective: to create a supervised machine learning model that utilizes 6 independent variables: loan amount, loan grade, loan purpose, income, age, and credit score, to forecast loan outcomes. Through feature selection, we pinpoint a subset of features that enables the model to perform nearly as well, or potentially even better, than one created using all 6 original features. Through feature extraction, we aim to apply a mathematical function to convert a dataset with high dimensionality into one with lower dimensionality. This process is similar to feature selection, where the end result is a subset of the original features. However, feature extraction produces a final set of features that are entirely distinct from the original set. The new features present projection of the original ones, which is why feature extraction is often referred to as feature projection. To demonstrate the process of feature extraction, let's assume we aim to develop a supervised machine learning model that utilizes the independent variables displayed here to forecast loan outcomes, which serves as the default dependent variable. Through feature extraction, we perform a mathematical transformation that generates 3 new features from the original data. This method is a highly effective strategy for dimensionality reduction. However, it does come with a significant drawback. As illustrated in this example, the value of the new created features can be challenging to interpret and might not be easily understood by users.